onto our topic of the day. We are continuing our discussion of polymers out of chapter 14. And before we get into looking at specific kinds of polymers, we want to look at some more polymer kinds of reactions. And so with this, we're looking at things like autopolymerization. Autopolymerization is a phenomenon where the building blocks of a polymer, all of those monomers, actually start to react with each other without the use of an initiator or some other kind of chemical startup. If you're familiar at all, you use diesel fuel for whatever kinds of purposes, other than just putting it into your car's fuel tank. That diesel fuel that sits around for a while has a tendency to kind of thicken up, gum up. And yes, you can put agents in there, chemical agents, to prevent that from happening. But what's going on there is that the diesel fuel is basically autopolymerizing. It's reacting with itself to form those gummy kinds of substances that make it so difficult to use if it's sitting in the tank for a long period of time. And so what you do in those situations, very similar to what you do with diesel fuel, is you put some kind of a chemical agent into it, an inhibitor, something that is going to keep those molecules apart from each other and keep them from reacting with each other. Because ordinarily, autopolymerization is not something that we want to happen, because it's going to give us products that we do not want in some kind of a capacity. So instead of making a particular type of plastic, all the monomers just end up clumping up together. They make the wrong type of material. Chemical inhibitors go a long way toward helping negate some of those processes. When these polymers are exposed to extreme heat kinds of conditions, they are liable to do one of two things. They will either decompose, or they will combust, or sometimes they will decompose and then combust. This can be the case for both natural fibers, things like wool, natural things like cotton, where you put them up to an ignition source, they just start burning. For others that are a little bit more synthetic, we tend to see melting take place. If you've ever exposed polyester to fire, it'll kind of melt and char rather than just ignite. Same thing kind of goes for plastics. Plastics usually kind of shrink up and melt rather than fully burn. And so what we will see in a lot of cases is the polymers themselves will kind of break down. They'll either decompose back into their monomers, they'll kind of melt, or they'll just kind of break down into some simple substances. And many of those simple substances end up burning in the fire anyway. So it really just kind of depends on what the situation is and what the material is. Most natural materials just go up in flames. Most plastic derivative materials, well, those tend to melt and char and do a bunch of other stuff. And you'll see some evidences of that in lab this week. As I mentioned previously, a number of materials will actually char. They'll singe and form kind of a carbon crust on top of the plastic as they burn. But the one thing that we'll see time and time again with these polymer materials when they burn is that they burn very, very exothermically. They generate tons of heat when they burn. Again, if you think about what they are from a chemical standpoint, they're carbon, hydrogen, and a small mix of some other elements. Well, we've seen from a number of different kinds of materials that hydrocarbon fuels burn. It doesn't matter if it's a little compound like methane, CH4, or a big compound like diesel fuel, which has up to 20, 25 carbons on it. The more carbons we add, the hotter it ends up getting. And so now we're talking about macromolecules that could have up to thousands of carbon and hydrogens on them. We can only imagine that if they got hot enough, and if they had access to enough oxygen to burn and burn successfully, we'd get some pretty hot fires as a result of that. And even if we don't get access to complete combustion, even in the incomplete, we still have lots and lots and lots of hydrocarbon to go through. And we know that every time a hydrocarbon burns, it releases a decent amount of energy. The more hydrocarbons we add, the more energy we're going to get. Now, because complete combustion is a rarity, given the size of these molecules, what we will usually see as a result of this burning is a lot of the byproducts of combustion. So in addition to the carbon dioxide and the water that come with every combustion reaction, complete or incomplete, we'll also get carbon soot, smoke, carbon monoxide. Depending upon what the other substances are that are attached to that hydrocarbon, we might get things like hydrogen chloride gas, hydrocyanic acid, if it encounters water, or hydrogen cyanide gas. We're talking about something like a nitrile. We can get vapors coming off of these as they decompose. They can create fumes that can be very, very dangerous to inhale. So one of the reasons we are talking about polymers kind of last here is because we see in polymers a lot of the other subgroups as these things decompose, as they burn, as they decay. We see the potential for corrosives coming out of these. We see the potential for oxidizers potentially coming out of these. We certainly see the potential for toxic materials coming out of these as they burn. And oh, by the way, they're still flammable solids, which have their own set of wonderfully complex problems on their own. Now, one of the side effects that happens as a result of polymer fires is a phenomenon known as flashover. Any of you here familiar with the idea of flashover? Well, you can read off the screen. The idea is this. As something is burning, so let's just say that you've got a couch that is on fire, and you've got it contained in a room. Well, as that couch is burning, it is going to be releasing tons of heat. I mean, that's the case when anything burns. But when you consider that a couch or any other piece of furniture is fabric, those fabrics are more than likely either polyester based or some other kind of synthetic fiber, or, I mean, even the case of things like leather, still something that's going to burn pretty good. You've got polyurethane foams making up the pads that you actually sit on. You've got a wooden frame, at least in good furniture. All of those things burn and burn really, really hot. Now you add that to the fact that we've got a lot of polymers that are on the surface of the couch itself, through the foam, through the fabrics, and you're going to recognize that not all of those are going to actually burn. Some of them are just going to get hot, start decomposing, and those decomposing vapors are going to start to fill up the room. Well, as the fire intensifies, those vapors become more and more concentrated as well. Flashover is basically the point where we've got enough of those flammable vapors in the room, and the room is hot enough in temperature that we hit the auto ignition point of the vapors. And we go from a fire that is just on our couch to a fire that is now engulfing the entire room. Because we've now hit the flash point, the fire point, the auto ignition point of those vapors on the other side of the room as the room is filled up with these decomposing polymer vapors. And this is when a fire in a house goes from being, yeah, this is a problem, to this is a big problem. We got to deal with this fast. We got to get our people out of there, because this whole floor might go up. And so I'm going to share a video of this, because I try to paint a word picture, but really it's better if you can see it yourself. So this video and I found it in YouTube, is a flashover demonstration for a fire company. And all fire companies have to go through this kind of demonstration training as part of their overall safety protocols and whatnot, and just preparing to be a firefighter.
So the fire's starting in a waste can in the corner. Yeah. So got a small flame just starting to flicker in there at this time. That's just paper products in a garbage can, as if a cigarette had been dropped in a garbage can, okay? You hear the smoke alarm initiating now, within seconds. Without that smoke alarm is what's buying you time to get out of that structure. Without the smoke alarm, you can see how fast it's beginning to spread. Now the corner of the couch is becoming involved. And once the arm of that couch is involved, you'll see the fire accelerate even more rapidly. You can now start to see some black smoke coming off of the flames. In just a second, that black smoke will be filling the ceiling, and you'll start seeing that black smoke begin to exit out of the structure.
All right, so I'm going to pause right here. You can see in this area here that black smoke has started to not only just form over top of where the fire is here, it is all over this area here of the roof. It's congregated in other areas. As they said in the voiceover, it's going to start ballooning out of the open structure that they've built here. And it's not going to take very long at all to get there.
You can see the smoke coming out of the front of the structure now. So hopefully, if you'd been home, you would have been able to exit your home already, dial 911. It takes about 2 minutes to make that 911 call and get the fire department on the road, and then it'll take us 4 or 5 minutes to get there. So about the same time that this room will be going to 1150 degrees, you hope that the fire department's arriving and extinguishing the fire. At this point, you'll see that the fire will accelerate exponentially every second.
Keep in mind, this is in an open atmosphere. So all that smoke that's kind of coming out of the front of the structure would be trapped inside of the home, which actually makes this even worse because all that soot contains also those vapors that are going to ultimately ignite here.
Y'all ready? On air? Okay, now watch the material across the couch. You'll see that the material will start melting and deforming as the heat comes down. When that material starts deforming, it's giving off gas vapor that will ignite. Now look up at the ceiling. You see the smoke burning at the ceiling now. So we're at about 1,000 degrees at the ceiling. And at this point, it's igniting see the little chair catch on fire? Go, 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 guys. Notice the carpet's on fire. There was nothing burning on the carpet. The carpet was heated up, began giving vapors off that will ignite, and when it went to 1,150 degrees, it all ignited. Okay, go ahead and knock it down, guys. So we hope that seeing is believing.
So that is the flashover effect. And so you saw it especially when they zoomed in on those couches and you could see that white smoke, that white vapor coming off of those couch cushions. That is what happens to polymers under high heat and stress, where they're not going to ignite right away. A lot of them are going to start to decompose first. And when they decompose, they're going to give off vapors, and those vapors will end up being flammable. And that's when we saw the fire go from something that was just over here, something that completely took over that room that they created. And we can see from this, we saw that fire really did start getting hot once the polymers got involved. And the main reason because of that is, well, it goes back to what we were talking about before. More hydrocarbons, more heat that can be evolved. Most common polymers can actually generate almost double the heat compared to a similar mass of wood. So we tend to think of wood as burning pretty hot, and it does. I mean, relative to our body temperature especially. But polymers, most of them will actually burn even hotter still. Right? I would be inclined to think that it would not have taken as long. I don't know how long. It wouldn't have taken as long to get to that part where the flames were just kind of billowing out. I think one of the things that you probably would have seen had there been a wall there, had there been windows there, is that the gas pressure inside probably would have caused one of those or several windows to blow and cause flames to start flying out of those windows as well. The pressure inside would have just been too great, because the thing you got to remember about combustion reactions is combustion reactions generate a ton of gas. If there isn't a place for those gases to go, then they're going to start pushing on the walls of their container. And if they start pushing hard enough, they're either going to move the walls, or if they're going to find a weak spot like glass and bust out that way to relieve the pressure. And that's when things will kind of, from the outside, look a lot more accelerated than they were before. Now, the main point of that particular video was to tell people that they don't have as much time as they think in their homes if a fire is starting. We tend to think of fire sometimes as being this thing that is kind of controllable, because based on our own experiences using fireplaces or fire pits. But if a fire starts in your home and you're not there immediately to put it out, then there are some problems that can evolve from that, and it can get very, very out of control very quickly. And that's where you either have to be fast thinking and take action. So while the fire was still in that trash can, if you had an ABC fire extinguisher in your home, you probably could have put out that fire before it spread anywhere else. But once it started to spread, there's nothing you can do. You had to get yourself out of it. And that was kind of the if you watch to the end of that video, and I'll link the video in the YouTube video that I'm going to produce for this. But it talks about making a fire plan, making a safety plan, having a good solid idea of how to get out of your house based on where you are in the house and where a fire is. Because, well, that's important anyway. You know, we teach our children from very early ages to have a family plan, to have a fire action plan, so that they can get out of their house safely if it were ever to catch on fire. Talking more about our combustion, we look at carbon monoxide. As you might expect, carbon monoxide, because of all those hydrocarbons that are all burning at this incomplete kind of rate, carbon monoxide is the most common gas at a fire. There's just not enough oxygen to turn all of that carbon into carbon dioxide. Carbon monoxide is going to be the most common, the most dangerous because of its concentration. Now, depending upon what the polymers are that are burning, we might also see other gases in play. So for PVC, for example, because of that chloride on there, hydrogen chloride gas is a common byproduct. Ammonia gas can be a common byproduct. Hydrogen cyanide can be a common product. Sulfur dioxide and nitrogen dioxide can be common products. The other thing, and you saw this in the video as well, did you see how much smoke was getting off of those fires? Even when it was burning hot, it was generating tons of black smoke. And again, the reason for that is incomplete combustion. We've got lots of carbons to burn and not nearly enough oxygen to actually convert them into gas. So we get lots of smoke as a result of those combustions. Now, there are some ways to combat the flashover effect. One of them is through a chemical treatment. It's hard to see in this picture because both mattresses seem to be on fire, but there are actually two mattresses in this picture. The mattress on the bottom was not treated at all. And as you can see, it is burned pretty significantly because we can see the interior springs of that mattress right here. There is actually a second mattress on this. It is on top of that first mattress. And this has been treated with a standard chemical treatment agent that basically allows the mattress to smolder at a slower rate than the bottom mattress does. And so when we look at the next image after the fire's been put out, we can see the difference. The mattress, yeah, it's got some charring on it on top. But for the most part, it's largely intact. I wouldn't use it again. But I also know that it didn't get burned up very much. The bottom mattress, on the other hand, well, you can see it's pretty black. It's pretty charred up. So that's one of the things that we can do. Chemical agents can kind of protect the polymers in certain types of fabrics by causing them to decompose more slowly, and as a result, they don't burn nearly as quickly. Let's move now away from the reactions themselves, and let's talk a little bit more about specific types of polymers. And so here, we're going to start by looking at some natural polymers. These are polymers that are derived from either vegetable or animal kinds of resources. So for example, cotton and linen, these are both derived from plant-based sources. And from these vegetables, for lack of a better term, we can derive fibers that are soft, yet strong, durable, yet light. Cotton and linen are great fabrics. Breathable. They're good all around. They've been in use for centuries now. They're good stuff. Wool and silk, these are animal-based fibers. Now, each of them have their own kinds of issues. Wool on its own can be kind of itchy, irritating as a fabric. It can be treated to be softer. Silk is more of a supply issue. Silk is derived from a particular worm, and well, there's just a limit on how many of those that can exist. It's also one of the reasons why silk tends to be more expensive because of, you know, the cost of acquisition for the fabric itself. Now, both of these can be altered and create synthetic fibers from them. And in some cases, that's exactly what we do. Whether it's to increase their strength, maybe increase their softness. There are a number of different directions that we can go with them. Another common kind of natural polymer is cellulose. Now, cellulose is found in pretty much every plant material that you can think of. Most plants have cellulose in them because cellulose is the primary component of most plant cell walls. So you think about what makes a plant rigid in its structure. Well, in most cases, it's the cell wall of that plant, if you remember back to your 9th grade biology class. And that rigidity helps it to get structure. That's why, you know, a plant can grow up and have a nice, you know, relatively stable stem, or in the case of a tree, the tree trunks themselves can grow up big and large and strong. It's the cellulose that ultimately gives it that structure and its strength. Now, for us, getting cellulose from plant materials is a little bit difficult because, well, we've got to separate it from all the other things that make a plant a plant. And so one of the ways that we can do it is, especially using wood. Wood's probably our biggest source of cellulose because, well, they're the biggest plants that we have most of the time. If we can find a way, either chemically or physically, usually chemically, to remove lignin, which is a natural binding agent inside of the wood, If we can remove the lignin from the wood, then that helps us to basically derive and get the cellulose out of it. Now, cellulose itself is made as one of those kind of starter materials for a lot of different industries. Paper, the wood industry, cotton textiles, where we take cotton and we add some cellulosic materials to it to give it certain kinds of structure. And the last one there, the cellulosic plastic industry, this has become a bigger one in the last 5 or 6 years. Cellulose plastics have been kind of one of the ways that we have derived to try to limit our ability and limit our use of crude oil for plastics. So if you've heard of the plastic bottle, or if you've heard of, there's a number of different kinds of shopping bags that are reusable that are going around, that are derived from cellulosic materials. That's what they are. Now, we're not talking about your cheap, let's go to Walmart and get 2 things and put it into a plastic bag. Those aren't cellulosic plastic bags there. Those are usually made from recycled other bags or from fresh stocks of plastic. But, the Coca-Cola industry has done a really good job of selling this plant bottle idea. They'll put it on all of their bottles to let you know that that's where it came from. But a number of companies have gone this eco direction to try to limit their use of new plastic materials. And there's actually been some research done where there's a particular type of plastic bottle. I don't think it's the same as the one that the Coca-Cola company is using. There's a plastic bottle that's actually being derived where the parts are actually supposed to be biodegradable. Where even if the plastic ends up in a landfill within a period of a couple of months, it basically disintegrates into nothing. That's supposed to be the idea. I don't know. It's been a couple years since I saw that article. I don't know if anything actually came of that, but I do know that that was something that was being worked on at the time. Wool and silk. Well, these are common animal fabrics. Again, we get wool primarily from sheep. We get silk mostly from silkworms. The fabrics here are actually derived from the proteins that come from the animals themselves. So wool is basically hair. The hair is a complex group of proteins. And the same thing for silk. These substances have an ignition temperature of 1058 Fahrenheit. So, one of the things that they were talking about in the video was what happens when we get to 1150 degrees Fahrenheit, how the room just kind of all goes up. Well, this is part of that. Now, other kinds of synthetic materials will go up at different temperatures, but that 1150 degree Fahrenheit temperature is kind of the mark that we look for in terms of hitting the auto ignition point for a number of different materials. All right, the majority of the remainder of our discussion in this chapter focuses on the vinyl polymers. Now, we've made a number of references to vinyl polymers over the past couple of days, starting with Friday. Remember, the vinyl polymers all have that carbon-to-carbon double bond in common, and we usually have hydrogens everywhere other than this one place right here. And that so-called R group is the thing that differentiates a number of the different vinyl polymers from each other. Now, these guys are super, super common. Pretty much all the plastic materials that you can think of are derived from vinyl polymers. And so the majority of our talk on Friday is going to be looking at these different vinyl polymers that exist and what kinds of applications and uses they get used for. We do know that the vinyl polymers are going to have a considerable part in both the plastics industry. All of our numbered plastics are derived from vinyl polymers, but also the textile industry, carpeting, curtains, drapes, upholstery on couches, chairs. All of those things have at their heart vinyl polymer characteristics. And so the first one that we will look at is polyethylene. Polyethylene is probably the most common of them. It's a pretty tight race between polyethylene and peat. Peat would be number one plastic. Polyethylene comes in two forms. It is number two plastic, high density polyethylene, and number four plastic, low density polyethylene. These are thermosetting materials. So again, remember the difference between thermosetting and thermoplastic. Once we mold them, they stay in that shape. And so while we do see some plastic bottles and containers that are in the number two and number four plastic variety, their thermosetting properties, their ability to not change shape, not to be manipulated too much, makes them really great for rigid kind of plastics like toys or things like rigid bottles like these. You have a Nalgene bottle, which those kind of rigid plastic bottles that are reusable, those are high density polyethylene as well. They are capable of being recycled, at least some of the forms. Number four plastics becoming harder to recycle based on where you live. What's interesting about these, in addition to their uses, we get more heat per gram than any other commercial polymer when this stuff burns. That's where we're going to close out today. Friday, we will finish this up, talking about all the other forms that are available and some of their common uses. Wednesday's our exam. If you have any questions about the prep, let me know. Have a good day. Next Wednesday's finals week. Yeah, 2 days from now.